Hey guys, Church of Thought here to talk about special relativity, which is really mass, energy, and time. Now, if you go on Wikipedia and you look up energy, you basically get kinetic energy, chemical energy, these different types, and they even do mention quantum mechanics, but they talk about it with regard to the Schrodinger equation. And I want to simplify special relativity for the layman. So what will follow is an explanation that I think everyone can understand. Now, if we go back in time to Richard Feynman, who worked on the atomic bomb, he worked on the Challenge shuttle explosion investigation. Very famous physicist, worked on quantum chromodynamics, quantum field theory. He had this idea. He said, okay, if I have this checkerboard, essentially, let's assume my universe is like a checkerboard. It's like a discrete pixels, like little cubes, right? And if we're just talking about 2D, then it would be basically like a sheet of graph paper. And he said, okay, if my universe is just made of these particles that all travel at the speed of light, right? And the thing is, in this model, this checkerboard model, not only is space quantized because you have individual jumps, each little pixel, right, each square, but you also have time quantized, right? Now, if you have both time quantized and both space quantized, and you say, okay, my particles all move at the speed of light. The fundamental particle, essentially, there's only one particle, right? It's called a monism, and it basically is the idea that everything comes from one thing. So if you just entertain this idea that everything is made out of a single type of particle that moves at the speed of light, then if it's on this grid, and if it's time is quantized, then essentially each particle will move one cell per time tick. That is effectively what the speed of light is on this lattice, on this checkerboard, this Feynman checkerboard. So, assuming that, you ask yourself a couple questions. You say, okay, now if all my particles are moving at the speed of light, right? That's the speed that they always move at. Then what does an object like me sitting here, look like on that grid? Like how does that stay still? I'm not moving. Well, I am moving technically, the Earth rotation and all that, but let's just assume there's an absolute reference frame, again violating relativity, but let's just assume I'm not moving. How would that be possible if all my constituent particles are moving at the speed of light? Well, the only way is if they're bouncing. So Feynman said, okay, if we assume all particles, the whole thing, the whole universe is made out of this one type of particle field, and these particles move at the speed of light, then the only way you get things that move slower, right? The only way you get essentially a resting mass, a resting object, is by bouncing inside of it. Not necessarily bouncing per se, but just some kind of cyclic movement that's burning up that movement, right? I could move at the speed of light, right? But if I'm going in a circle, then I'm not going anywhere. There's no net movement. So, you have this relativistic concept, and when it comes to what is mass and what is energy, especially when you're talking about relativistic mass. Because if I weigh an atom, I'm weighing essentially the energy of the electrons moving around in that atom. The mass that I'm getting on the scale also is accounting for the bonds between the quarks. All that energy is basically being measured. And so when you put a object of a certain mass on a scale, right? Now, if all objects are made out of particles that move the same speed, then the speed of those particles is irrelevant, right? Essentially, the relativistic mass of an object, essentially what it will be when you put it on a scale, is just the number of those particles. So if I'm made out of, let's say, 1,000,000 of the, obviously that's not the case, but if I'm made out of 1,000,000 of those particles and I'm sitting still, then those 1,000,000 particles must be bouncing and somehow bound up, you know? They're not bursting forward like an atomic bomb. Now, in the case where I have an object, let's say a spaceship, moving at the speed of light, what does that look like? What do its internal constituent particles look like? Well, it's moving at the speed of light, and those particles naturally move at the speed of light. So it's essentially going to look like this. You know, we're going to basically, if this is my spaceship is going to be all of its particles are moving parallel to whatever its velocity is, right? They're just moving straight. There's no bouncing, right? You know, this is the spaceship, right? Every single particle inside of it is just moving towards the direction it's moving at the speed of light. Now me, on the other hand, I'm sitting here, right? You know, this particle is moving this way, and then it bounces into this one, and then it bounces into that one, and so on, such that there's no net movement. But when it comes down to it, the mass, if this is made out of 1,000,000 particles, and this is made out of 1,000,000 particles, they both will have the same exact relativistic mass. The only difference between the two is, of course, the rest mass. So, rest mass becomes an emergent concept in this view. Basically, just the rest mass is the amount of bouncing inside of an object. You say, okay, what is, this particle's rest mass? I say, okay, well, if that particle were basically at rest, how much bouncing is going on inside of it? Because effectively, that's all, that's the total number of particles inside of it is the relativistic mass. The amount of bouncing inside of it is the mass, and its velocity, right, is basically that difference between the two. So let's talk about that difference. Now, if I have a spaceship, right, this one was moving at c. It was moving one pixel per second, right, speed of light. Now, if I have another spaceship, and let's say this one's moving at c over 2, right? So what kind of dynamics would we need for this spaceship not to move fully at the speed of light, but at half the speed of light? Well, you could divvy it up like this. Half of the time steps, again statistically, half of the time steps the particles are moving, they're shifting globally in the direction of its velocity, right? Now the other half of the time steps, they're bouncing internally. And here's where you get time dilation. Again, part of special relativity. The amount of time dedicated to the internal bouncing, right, is mass, is essentially the rest mass, right? And is also the amount of local time being spent. So the mass is related to the local time because of that. If there's no bouncing inside this object, for example, this spaceship on the left, right? What happens to each particle every time tick? All it does is shift toward that direction that the spaceship's moving. It has no opportunity to change. None of the particles of that spaceship have any opportunity to change at all. All they do every time tick is just move. On the other hand, the one moving at speed of light over 2, half of its time ticks, right? Those particles can internally, bounce and internally interact. And the other half, again, statistically, doesn't have to be, knitted like on time step 1, they bounce. On time step 2, they move up on time step 3, but essentially it's a statistical nature, the ratio of internal bouncing versus global shifting. And so, you've got half of the time ticks dedicated to one thing, half of the time ticks dedicated to the other, and that's why you get the time dilation. Locally, if there's no internal bouncing, then nothing can happen internally and locally. So the time essentially is infinite. That's why a photon is essentially ageless. It doesn't experience time. And that's why when an object speeds up, more and more of its essentially the energy that object possesses becomes dedicated to moving it. And it's a common, mistrope in physics to think of movement, right, or position as something other than state. What energy does is essentially anything that possesses energy can cause a change of state. If something can't change any state, it doesn't exist. It doesn't possess energy. So it's kind of, that's the shit test for for what is energy or what contains energy. If something can cause a change in state, a change in information, then it possesses energy, right? And so the energy that an object possesses basically gives it what's called action. And so if we look at quantum action, for example, like Planck's constant, right? Essentially, action they talk about with the Lagrangian and with the Hamiltonian and whatnot, but the unit of it is energy times time. And the reason is because given a certain amount of energy, right, that an object possesses, that object, right, those particles that possess that energy are going to basically have to change state so many times per unit unit time. So for example, on this spaceship on the left, I know how crudely drawn this is, but each particle inside of it, essentially its energy lets it move 1 cell per second globally on the grid in the direction of its velocity, the spaceship's velocity, right? That's how that energy is being burned up. Those are the actions that are being committed. The energy entitles that energy that each particle possesses. And remember, it's a monism. All these particles are essentially the same. They all move at 1 cell per second on this pixelated grid, so they all possess the same energy. So if you want to know the total energy inside an object, you just count the number of those particles, right? And when you talk about rest mass and relativistic mass, then you have to get into bouncing. But in any case, we have so many particles inside this object. Each one will move 1 cell per second. That burns up that energy that it possesses. That energy has to be conveyed by change of state. Now, if we look at the object that's moving the speed c over 2, speed of light over 2, half of those, essentially that energy entitles the object to an action per second. Each particle essentially has to do a single change of state per second. Now that can be a global shift, right? Or that can be something that involves bouncing. You can even extend the model, Feynman was really, he talked about bouncing, right? But you can extend the model and include interaction. The point is, special relativity, what it's really saying is that global movement is orthogonal to interaction or local movement, local bouncing. So you either get one or the other. You don't have both at the same time. So essentially the energy of an object has to be divvied. It has to be split between doing local things and doing global things. And special relativity, when you talk about time dilation, you're talking about movement, right? You're talking about the change of state when it comes to movement, because we're talking about velocity. We're talking about change of position, right? So a global change in position is orthogonal, it's conjugate, to a local interaction, or if your model doesn't have, let's say, interactions, if it's as simple as, Feynman's interactions as just local internal bouncing, right? Then it's really just a divvy up between global shifting of a particle and then internal bouncing. And so you're really talking about, okay, these actions that this energy permits, how are they divvied up? That's all special relativity is. And so you get these very elegant concepts from such a simple way to look at it. And essentially, it's called doubly special relativity. What Feynman was kind of getting at with the checkerboard, it's saying that energy, this idea that there's a monism, essentially a single particle that everything is made out of, and it's essentially it's quantizing energy, saying that energy not only because when it comes to quantum physics, you talk about a photon as a quanta. For each frequency, there's a different energy photon. But here, doubly special relativity goes further and says, okay, well, the energy itself has a smallest chunk. And so it goes hand in hand with this idea of the Feynman checkerboard, and there being a single type of particle, and everything being made of that. So, anyways, back to the kind of grand kind of nutshell over here. We have mass, right? Rest mass particularly. And rest mass simply being the amount of energy that is being burned up by some kind of cyclic process. Now, Feynman says that's the internal bouncing, if you just look at the universe as purely kinetic. But in any case, it's the idea that the energy causes a change of state, a fixed amount of changes of states per unit time. That's what energy permits, right? And that energy, essentially, or rather, the mass represents that energy being burned up without or rest mass represents that energy being used without a global change in position, without a global change in state. So some kind of cyclic process. Now you don't have to believe that, it's simply things bouncing. You don't have to believe the universe is purely kinetic, because it could be changes of chemical state. It could be any kind of changes of state that just aren't bleeding out into actual global movement. And that would essentially allow the object to possess that energy and not move, because that energy is being used in a cyclic change of state that doesn't involve global position. Okay, so essentially the big point is that change of position globally is a change of state. That is a usage of energy. Given an object with a fixed amount of energy, that object must divvy it between basically mass and between movement. And any way it divvies it up, that's why you get objects with different rest mass. Photon essentially has no internal energy, like there's no energy being burned up internally. All of it is causing movement. All of it is causing global movement for that photon. There are other objects, depending on what they are, like an electron orbiting a certain atom at a certain drift velocity, may have a different scenario. But we do know that certain objects they have certain rest masses by comparing different scenarios that they're in. But anyways, that's the idea. How much, when the object is essentially at rest, how much energy is stored inside that object being used in a cyclic fashion. Okay, we've got mass. Now we've talked about energy. Again, energy just permits a certain amount of state changes per unit time. And that's all it really is. A photon, for example, a single photon. right, moves. If you believe in, if we take the Feynman Checkerboard model and say it moves, okay, 1 tick per second, one little, cell on the board per clock cycle, then that's its change of state that it's using, and that's its conveyance of that energy that it possesses. That's all it is. It just allows a change of state. Now, you can look at that, and kind of realize, okay, well, look at an atomic bomb. What happens with an atomic bomb? You have all this energy bound up, right, as mass, as rest mass, right? And you can even look at it as the kinetic model, like Richard Feynman's kinetic model. There's all this energy, but it's bound up in these particles that are bouncing. So it's sort of like you have a race car and you tied, you tied the car to a pole, right? And it's essentially, there's a rope here and there's a car, and the car's going round and round and round and round, right? Right? It's just going round and round, but it's tied to this pole. So is it gonna go anywhere? No, right? So there's some stability. Essentially, mass has to have some stability. Some mass is unstable. Talk about radioactive elements, but essentially that energy is bound up, right? That movement is essentially bound up, right? It's being used. The states are changing, but it hasn't bled out into other fields. It hasn't bled out into global movement field. It hasn't bled out, let's say, into the electromagnetic field or any of the other fields. It hasn't expressed itself. It's essentially stored, as this, it's stored inside this object. And now, of course, when in an atomic bomb, you basically set off a chain reaction, which causes instability, which causes the atoms to start to break apart and release different parts, beta decay or gamma decay and alpha decay, and essentially pieces of them, electrons, protons, neutrons, start to come off, right? And they're going at a certain speed, they're taking some of the mass with them as well as the energy, or as well as, they're going at a certain speed, so energy is coming away. Energy is essentially, coming away because that stability has been ruined. So, that's a good way to see it. You essentially, rest mass is kind of bottling up that energy. It's bottling up that state change. And finally, when you upset the stability, that state change, right, gets released into all these other fields. And then you can clearly see the state change. You see the mushroom cloud. You see the explosivity. Now you see all that energy, those state changes. They were bottled up real tiny, but now they're not. They essentially aren't, local anymore. They're not localized. They become global movement. They become, electromagnetic radiation, electromagnetic pulse that fries all the electronics and the heat and, all these other things. So that's the energy side of things. And then, of course, you have the time side of things. And, of course, the time just relates to the way that the energy is essentially, what the energy is and how that relates to the mass. The time, time basically sets the stage. It says, okay, for a given amount of energy, that energy can basically change so much states per second, per time tick. And those state changes are going to need to be divvied up between local change inside of an object and global change essentially outside of the object. And so you basically get time dilation, and you get the idea of local time from the way the energy is, split up. The actions are split up. If you're using 9 out of 10 of the actions that the energy permits to do local things, you'll have a lot more local time. right? You won't be moving much. Now, if you use all the energy that your permits, essentially a photon, for example, this spaceship on the left that moves at the speed of light, there will be no time. That spaceship will not evolve. Anyone in that spaceship will not change at all. It's as if this thing is just totally being shifted. It has no evolution at all, right? So I hope this explains special relativity in a more, more conducive way. It's really very simple if you look at the universe a bit more from an informational perspective and especially from a kinetic perspective, but you don't necessarily need to buy in to the idea that all energy is movement. It just helps illustrate the point. The real thing to nail down is that local interactions or local, essentially, movement is complementary, it's orthogonal to global movement and global change. If you do one, using the energy that an object, if an object does one using the energy that it possesses, then it has less time to use that energy for the other one. And so that ratio between the two gives you time dilation. The ratio between the two gives you what the rest mass of an object is. And yeah, that's special relativity. It all really just follows very simply from doubly special relativity and this, Feynman checkerboard, and sort of this this monism of one type of particle. But there are other ways to formulate it. I just find that this way really kind of nails it down and makes it much easier. No Lorentz Transforms, none of that shit. It's just very simple. Mass, energy, and time are entirely related. They're just basically reliant on each other. And if there is going to be a grand unified theory eventually, it's going to have to take these things into account. So hope that helps. Let me know if you have any questions. Let me know if you have any thoughts. Church of Thought, signing out.